Rubidium has two naturally occurring isotopes, rubidium-85 with a mass of 84.9118 U and rubidium-87 with a mass of 86.9092 U. If the atomic weight of rubidium is 85.47, what is the relative abundance of rubidium-85? So before we start solving this, let's refamiliarize ourselves with a few things. Carbon on Earth is found in three different, let's call them versions. So we have three different versions of carbon. We have carbon-12, carbon-13, and carbon-14. All three of them have the same atomic number, 6. So they have the same number of protons, and that's what makes them carbon. The difference lies in their mass number, which is the number of protons plus the number of neutrons. So you have an increment in the number of neutrons as you go from carbon-12 to carbon-14. When you look at carbon given in the periodic table, you see that the mass number is not exactly an integer value. You have 12.01. So how can there be, a fraction numbers of neutrons? What is going on? This number given in the periodic table is not the mass number, but it is the average atomic weight of the element. The average atomic weight is defined to be the weighted average of all the isotopes of that element. So you have this equation that says that it's the sum of the atomic mass of the isotope times its ratio abundance. The atomic mass is given in Dalton, or the Unified Atomic Mass Unit, and what I mean by ratio abundance is that the percentage abundance of that isotope will be given to us as a ratio. So say you have 58% of some isotope, that would be written as 0.58, so it's as a ratio. So let's get back to this question. We know that the average atomic weight of an element equals the sum of the atomic mass of an isotope times its ratio abundance. What this basically means is that it is the sum of the atomic mass of the first isotope times its ratio abundance plus the atomic mass of the second isotope times its ratio abundance. And this basically can keep going on depending on how many isotopes you have. So for rubidium, we have two isotopes, so I'm going to stop here. We have the atomic mass of rubidium-85 times its ratio abundance plus the atomic mass of rubidium-87 times its ratio abundance. It's going to be the sum, which will give us the average atomic weight for rubidium. So let's write down what we're given. We have the mass of the isotopes, the percentage abundance. The two isotopes are rubidium-85 and rubidium-87. So the mass of rubidium-85 is given to us as 84.9118 U, and the mass of rubidium-87 is given to us as 86.9092 U. We are also given the average atomic weight of rubidium, which is 85.47 U. The equation that we're going to use is atomic weight equals to the atomic mass of the first isotope, that's rubidium-85, times its ratio abundance plus the atomic mass of the second isotope times its ratio abundance, right? I think you can see pretty clear right now where we're going to get stuck. We don't have either of the percent abundances for two isotopes, so we have two unknowns in our equation. So how do we go about solving this? What we can do is that we can define rubidium-85 to have a percentage abundance of X, right? We can say that rubidium-85 has X percent abundance. By the definition of percentages, we know percentages are out of 100. So by definition, the percent abundance for rubidium-87 will be 100 minus X, right? So these are going to be the variables that we will plug into this equation down here. So let's get started. So we have the atomic weight given to us as 85.47. This equals to the atomic mass of rubidium 85, pardon me, and that's 84.9118. The percent abundance that we defined would be X, right? Now this is going to be added to the atomic mass of the second isotope, which is rubidium 87, and that's 86.9092U. And we defined the percent abundance to be 100 minus X, and that's going to go in square brackets. Now you may have noticed that I have not used ratio abundance. Rather, I'm using the direct percent abundance, because it would make the math much easier if we do it this way. Either way, we would get the same answer. So because I'm using the percent abundances, I'm going to divide this entire thing by 100. Let's get a bit of more space here. So bringing 100 to the other side, I would get 85.47 times 100. And then we are going to solve our brackets. We're going to get 84.9118x plus 8690.92 minus 86.9092x, right? So we get 8547 equals to 84.9118x minus 86.9092x plus 8690.92. Let's bring this to the other side, and we would get 8547 minus 8690.92. This equals to 84.9118x minus 86.9092x. And now we can finally solve. So we get minus 143.92 equals to minus 1.9974x. So the negative signs get cancelled, and we get x equals to 143.92 divided by 1.9974, which equals to 72.05%, right? We defined the percentage abundance of rubidium 85 to be X, and we calculated it to be 72.05%. We defined the percent abundance for rubidium 87 to be 100 minus X, and that would give us 100 minus 72.05, and that would be 27.95. And there you have it. Even though the question just asks us to find the percent abundance for rubidium 85, it won't kill us to give it for rubidium 87 as well. Let's check our answer intuitively. We were given the atomic weight of rubidium to be 85.47, and we calculated the percent abundance of rubidium 85 as 72.05 and rubidium 87 as 27.95. The clue lies in the atomic weight given to us. Since 85.47 is closer to 85 than it is to 87, we have a pretty good idea that the percent abundance is higher of rubidium 85 than it is of rubidium 87. What this means is that the isotope rubidium 85 is present in a greater quantity than rubidium 87 is. And that's what our answer also reflects. The percent abundance calculated for rubidium 85 is much higher than it is for rubidium 87. So this is one way we can see whether our answer makes sense, whether it's correct or not.